Welcome back, students. In this video, we'll discuss intermolecular forces. These are the types of forces that hold like molecules together. Now, we're going to talk about in this video what makes molecules alike or different. So the stronger the attractive forces among different molecules, the more they're going to resist moving away from each other. And this can also help determine the state of the material as well. All molecules that are above absolute zero, which is, by the way, impossible to attain, are in motion. All molecules are in constant motion, but the motion is going to depend on the strengths of the intermolecular interactions and the temperature of that particular system. So the strengths of the attractions among particles is going to help determine its state. At room temperature, we usually observe moderate to strong attractive forces in materials, causing them to be liquids or solids. But there are, of course, gases at room temperature as well. The higher the attractive forces are in materials, the higher the boiling point of the liquid will be and the melting point of the solids. So why are molecules attracted to each other? Let's consider water, for example. Here are some molecules of water, and we can see the oxygen represented in a red sphere and hydrogens represented in the white spheres. So the bonds are these little sticks holding the molecules together. So these are two molecules of H2O. Now, we're going to talk more about this later, but water is unique in that oxygen is the second most electronegative element on the periodic table. So you see here oxygen right next to fluorine. And because oxygen is so electronegative, it's going to withdraw electron density from the hydrogens, drawing electron density toward itself. That's going to leave the oxygen with a partial negative and the hydrogens with partial positives. So this is the main type of intermolecular interaction that we observe in water, which is called hydrogen bonding. And again, we're going to talk more about that in a later video, but these partial negatives and partial positives are strong forces that actually encourage the water molecules to stick together. Okay, we call this polarity when molecules have a partial positive, partial negative end. Hydrogen bonding is a specific type of polarity that is stronger than most other types of polar interactions. All right, so we have several different types. So we're going to look at this in a chart in a few minutes. We have a type called London dispersion forces, dipole-dipole interactions, and hydrogen bonding. We also have ion-dipole interactions and ionic bonding that exists in molecules. First, we'll talk about London dispersion forces. So these are the forces that are available in all molecules, and what they result from is the normal motion of electrons within the molecule. So sometimes the electrons may be hanging out on one end of the molecule, and other times other ends of the molecule or atom, for example. Here's a little example of that. So here we have atoms represented with their electrons orbiting the atoms, and at one instant in time the electrons may have this configuration, at another instant they may have this configuration, and at another instant they may have this configuration. So the electrons are constantly moving around the atoms, and the region of electron density that has more, or the region of the atom that has more electron density may exhibit a partial negative charge, and the region of the atom that has less electron density will exhibit a partial positive charge. So these are very brief-lived dipoles that are created in molecules from the normal distribution of electrons. And this also happens because molecules are bumping into each other, and when a atom or molecule bumps into another atom or molecule with partial negative end, these electrons will repel each other and push the electrons to the other end of the atom. And so, due to normal motion of electrons and the movement of atoms, these dispersion forces are created as instantaneous and brief-lived forces that cause negative and positive charges to exist on different places in the atoms or molecules. Okay, so these are called instantaneous dipoles that exist in atoms or molecules. So you can see here from this helium atom that we have a partial negative from the distribution of more electron density on, in this case, the left end of the atom, and a partial positive from that lack of electron density on the right end of the atom. And that comes because there is a positive charge in the nucleus, so that positive charge is more evident when it's not being shielded by the electron density. The partial negative then builds up on the next neighboring atom and so forth, and so that helps to hold the atoms together. These are the weakest of the attractive forces, but they exist in all materials. Okay, so the size of that instantaneous dipole will increase with polarizability of the electrons. So if it's a larger volume of the electron cloud, it's going to be more polarizable. In other words, larger atoms are going to be more polarizable, and that will increase that instantaneous dipole. Also, larger molecules will have a larger van der Waals interaction. This is called a van der Waals interaction. And the shape of the molecule will also affect the strength of this interaction or the magnitude of this interaction. So the larger the atom, meaning the further down on the periodic table, the more polarizable the atom is because it's going to have more electrons. And a larger atom compared to a smaller atom, all other factors being equal, will have a larger instantaneous dipole or van der Waals interaction. A longer molecule versus a shorter molecule, the longer molecule is going to have more electron density around it, and therefore more surface area for these interactions to occur, and therefore the longer molecule will have more of these interactions, all right, versus a shorter molecule, all other things being the same. Also, a molecule that has a shape that is clumped up versus spread out, okay, all other factors being the same, the spread out shape will have more instantaneous dipole forces or van der Waals interactions. Okay, so we can see that demonstrated here with comparing the noble gases. These noble gases are not particularly electronegative. They don't have any other real factors holding them together. But we see that the increase in molar mass, which increases the electron cloud because we have an increase in the protons in the nucleus, we have an increase in the electron cloud to balance that out. So the increasing molar mass, you can see, is increasing down the column on the periodic table, increases the boiling point along with it. So helium has and this is in Kelvin, has a boiling point of 4.2, neon is 27, argon is 87, krypton 120, and xenon 165. So these are all still gases at room temperature, but their boiling point increases relative to the size of the electron cloud around those atoms. All right, and so the stronger the attractive forces are, the higher the boiling point will be. Now, we're looking at examples of molecules or atoms that only have these London dispersion forces, which are also known as van der Waals interactions. Okay, these molecules only have these dispersion forces available. And these dispersion forces are available in all molecules. But if we have other forces available, the strengths of those interactions generally effectively cancel out the strength of the dispersion forces because they aren't significant compared to the strengths of the other interactions. Here we have N-pentane on the left, which has 5 carbons. Okay, you can see that it has a molar mass of 72 grams per mole and a boiling point of 36.1 degrees C. On the right we have neopentane, which is an isomer of N-pentane. It has the same molar mass, but it's more clumped up. It's more spherical. So we don't have as much surface area in this molecule for the dispersion forces to be as effective. Okay, and so we have a noticeable difference in the boiling point. It's much lower because it has a lower surface area. So you can see that demonstrated, a similar trend demonstrated in the alkanes. So these have different molar masses. We're going from 5 carbons to 6 carbons to 7 carbons to 8 carbons to 9 carbons. And you can see that as the molar mass increases, or we could think of this as the carbon chain lengthening, the boiling point increases as well. So as the carbon chain gets longer, and these are all long carbon chains. They aren't clumped up at all, so we're just comparing the length of the carbon chain, the number of carbons here. The boiling point increases respectively. So branch chains, with all else being equal, have lower boiling points than straight chains. And straight chain isomers have higher boiling points because they have more surface-to-surface contact. So in other words, if all the carbon, if they are isomers of each other, the carbon chain length is the same, a more spread out molecule will have a higher boiling point than a more compact molecule. So let's consider the halogens here, chlorine, bromine, and iodine. Chlorine, bromine, and iodine. Which of these has the highest boiling point? So iodine does, because it's a larger molecule. It has larger atoms and therefore is more polarizable. The next intermolecular interaction we'll consider are the dipole-dipole interactions. So these still have the London dispersion forces available. These molecules still have electrons in a cloud around the atoms, so they have those London dispersion forces, but they have an additional type of interaction called a permanent dipole or a dipole interaction. Okay, and this is dependent upon the bond polarity and the shape. Okay, so we talked about this a little bit in chapter 11. We talked about dipole moment in a molecule, and we talked about how the shape of a molecule affects that. And you see here a molecule of acetone. So this is the structural formula for acetone. This is the space-filling model and the electrostatic potential map. You see that more electron density is hanging around the oxygen, and that's because oxygen is the second most electronegative element on the periodic table. It's pulling electron density toward itself and away from the neighboring carbons, leaving these carbons with a partial positive and the oxygen with a partial negative. And you can see that demonstrated in the electrostatic potential map. Now that's a permanent dipole. It isn't going to go away as the molecule moves around. It's always going to have that positive and negative end of the molecule. And if you considered how these might line up in solution, the partial negative ends will align themselves with the partial positive end of the neighboring molecule. Of course, they're always moving around, and these bonds are weak. They're not covalent bonds. They're intermolecular interactions, and they're going to be constantly breaking and reforming. But the strength of these interactions is greater than the van der Waals interactions that we saw earlier, or the London dispersion forces as they're also known. So it causes a higher boiling point relative to a molecule of the same size that doesn't exhibit these types of interactions, as we can see here. We have formaldehyde at the top and ethane at the bottom. They have a similar molar mass, but formaldehyde has that permanent dipole, and we see that its boiling point is negative 19.5 relative to ethane, which is negative 88. You can see here that with all other things being equal, all of these molecules have about the same molar mass. As the dipole moment increases, and we see that measured here along the bottom as dBi, as the dipole moment increases from 0.08 to 1.3 to 1.89 to 2.69 to 3.92 dBi, the boiling point also increases as well. These attractive forces will also affect solubility of molecules. So like dissolves like, and polar molecules are soluble in each other. Nonpolar molecules are soluble in each other, which is what leads to immiscible liquids. For example, pentane here is a nonpolar molecule, and it doesn't dissolve well in water. It will actually float on top of water because it's less dense. Water is a polar molecule, and the attractive forces in water will hold these molecules together relative to something like pentane that is nonpolar, and that keeps these molecules separated because the attractive forces in the water are strong enough to push out the pentane, and since it's less dense, it floats on top. Earlier, I alluded to an intermolecular interaction called hydrogen bonding. This is probably the most important intermolecular interaction that we observe. We observe it when hydrogen is bonded to an electronegative element like oxygen or nitrogen. Fluorine also counts, but HF is in itself an entity, and we don't observe hydrogen attached to fluorine within molecules. So HF is used for just demonstration purposes, but for the most part, hydrogen bonding exists when a hydrogen is covalently bonded to an oxygen or a nitrogen. So if we look at these two entities on the periodic table, we'll see that oxygen is the second most electronegative element as electronegativity increases from left to right and from bottom to top on the periodic table. So fluorine is the most electronegative, oxygen is second, and then nitrogen is next to oxygen. And that's why when we have hydrogen bonded to one of these atoms, we observe hydrogen bonding. So because hydrogen has no other electrons, when its electron is being pulled away by a more electronegative atom, the nucleus becomes de-shielded, which exposes the proton there and leaves a partial positive charge. And this partial positive charge is really stronger than the partial positive that generally exists when we have just a regular dipole in a molecule. So hydrogen bonding is a dipole-dipole interaction, but it's unique in that it is stronger than a normal dipole-dipole interaction. Here we have HF, so we have hydrogen bonding demonstrated with HF. So we have fluorine being the most electronegative element on the periodic table, and its electron density is it's pulling electron density away from the hydrogen. So we have a partial negative on the fluorine and a partial positive on the hydrogen. And again, this is stronger than just a normal dipole. So we see the partial positive and partial negative ends of these molecules aligning. And this, even though this is not a covalent bond, this is a very strong interaction between these molecules. So here we observe hydrogen bonding in water and in ethanol. So ethanol is an organic molecule which can also have hydrogen bonding, an OH group on an organic molecule. An organic molecule is a molecule that is generally comprised of carbon. So if we have an OH group on an organic molecule, that's called an alcohol group. So there are different alcohols, but the most well-known alcohol is ethanol. This is the alcohol that's found in alcoholic beverages that some people drink. So here we see oxygen with a hydrogen attached to the oxygen. The oxygen, being the second most electronegative element on the periodic table, is withdrawing electron density from the hydrogen, pulling electron density toward itself, and leaving a partial positive on the hydrogen and a partial negative on the oxygen. Now you might say to yourself, why is this carbon-hydrogen bond here not considered a hydrogen bond, right? And that is because the carbon-hydrogen bond doesn't have a large enough difference in electronegativity to be considered a polar bond. A hydrogen bond has to be a polar bond in order for there to be a partial positive and a partial negative effect. Okay, so that makes these molecules soluble in each other, and it makes them more strongly attracted to each other and raises the boiling point relative to other similar, even isomers that are nonpolar. All right, over on the left we see water, and water is a very unique molecule. It's important for life all over the earth, and we have a partial negative on the oxygen, partial positive on the hydrogen, because we have these hydrogens, two hydrogens, covalently bound to the oxygen. The oxygen is withdrawing electron density from the hydrogens, leaving a partial negative on the oxygen end and a partial positive on the hydrogen end. So these molecules will align themselves in such a way that the partial positive and partial negative ends are aligned with each other, forming a network of bonds throughout the whole system. And this raises the boiling point relative to similar molecular weight molecules that don't exhibit hydrogen bonding. Also, like dissolves like, and these molecules are actually soluble in each other. And in fact, ethanol is miscible with water because the carbon-hydrogen end of the molecule is so small that it isn't large enough to negatively affect the solubility. So hydrogen bonds are strong intermolecular interactions. Again, they're stronger than dipole-dipole or dispersion forces. Even though dispersion forces are present in these molecules, they aren't the main interaction that we consider, and they aren't the main interaction that's going to contribute to the boiling point or the solubility. So hydrogen bonds are not as strong as covalent bonds. They're only about 2 to 5% the strength of covalent bonds, but they are important interactions. You can see that demonstrated here comparing ethanol to dimethyl ether. So these are isomers of each other. They're structural isomers. They have the same molecular formula, but because of the way the atoms are arranged, they have wildly different boiling points, because ethanol exhibits hydrogen bonding because it has a hydrogen bound to the oxygen. However, dimethyl ether doesn't have a hydrogen directly bound to the oxygen and therefore doesn't exhibit hydrogen bonding. We can see that the molar mass is the same since they're structural isomers of each other, but the boiling point of dimethyl ether is -22 and the boiling point of ethanol is 78. So hugely different. We have a 100 degrees C difference in the boiling point roughly here, but these actually have the same atoms. They're just connected differently. So hydrogen bonding is a huge effect here. And dimethyl ether is a polar molecule, but it doesn't have the hydrogen bonding type of polarity. All right. So we see here hydrogen bonding in ethanol in an electrostatic potential map. We see the partial negative end of the molecule near the oxygen. The next type of interaction we're going to consider is an ion-dipole interaction, and these are generally important in solutions where we have salt molecules. Okay, so if we have, say, sodium chloride, which you know dissolves in water, that's table salt, it dissolves in water. Why does it dissolve in water? Because the interaction of the positive and negatively charged ions is large enough with the water to overcome the intermolecular interactions between the sodium and chloride ions. So we can see here the sodium ion is positively charged, and the positively charged sodium, let me draw that out over here, is going to be surrounded by a solvent shell of the water. And remember, water has hydrogen bonding, so we have partial negative here, partial positive here, okay? And so that intermolecular interaction allows the sodium to be soluble in the water. Now, not all ionic salts are actually soluble in water, even though they have these positive and negative charges. And that's because the strength of the interactions between the ions can be greater than the strength of these polar interactions can overcome. Okay, but we form a solvent shell around the ionic species, okay? And that is going to allow the sodium ions to be dissolved by the negatively charged end of the water molecules. And likewise over here we see the chloride, which is negatively charged, and it will be surrounded by the positively charged ends of the water molecule, which has the hydrogen bonding. So, like dissolves like, these ionic compounds are soluble in water because they have positive and negative charges, which can be surrounded by the partial positive, partial negative charges in the water. So in summary, the dispersion forces are the weakest of these intermolecular interactions. They're present in all molecules and atoms. The magnitude of the dispersion forces, the London dispersion forces or van der Waals interactions, increases with molar mass. Polar molecules have dipole-dipole attractive forces. Hydrogen bonds are the strongest of the intermolecular interactions that don't have ionic species. Okay, hydrogen bonds are present when a molecule has a hydrogen directly bonded to an oxygen or nitrogen, or in the case of HF, to a fluorine. Ion dipole interactions are present in mixtures of ionic compounds with polar molecules. And ion dipole interactions are the strongest intermolecular interactions that are present in generally aqueous solutions, which is where we're going to see them mostly. So here we have a chart of these different types of interactions. We have the dispersion forces. Okay, we have the dipole-dipole interactions where we see the positive and negative charges lining up. We have hydrogen bonding, and then we have ion dipole. So if you take biochemistry, you're going to see all of these interactions demonstrated in the types of interactions that we'll see in proteins or in protein ligand interactions. So this is just an introduction for you to these interactions that you're going to see more of as you move through your chemistry courses.